Today, we, we will talk about the fatigue failure and rotating bending fatigue test. That is most common fatigue that we have. Fatigue failure happens when the materials breaks after being exposed to repeated cycles, means dynamic loading, not static loading, of stresses or strains over time. Even if the maximum stress is below the yield strength or sigma y. Repeated loading can eventually cause cracks, form and crack propagations and crack grow until the part fails. This type of failure is very common in mechanical components such as shaft, axles, and aircraft parts, and it occurs for almost 90% of mechanical failure. So, fatigue is very important because we expect that when stress reaches to sigma ut or ultimate tensile stress or something, we expect that failure starts, but in loading conditions, it will occur in sigma less than that, or maybe less than yield stress. Okay, what is fatigue failure? Fatigue means failure under a lengthy period of repeated stress or strain cycles. And you see in this image the meaning of the repeated. That means stress is not constant. From this amount reach to maximum here, so it is sigma max and it is sigma mean, and you see that it is the periodics completely. So fatigue means failure under repeated stress or strain cycling over the time. Stress varies with time, as you see sigma change to sigma max and again decrease to sigma mean and back to initial value. So if we want to write that, we can say, okay, sigma is the S. S here consider the amplitude of stress, sine omega t plus theta. That omega is angular frequency, that is 2 pi f. And f is frequency and f is reciprocal of period. What is the period? If you consider this point, what is the equivalent of this point in the next cycle? It should be this. So the change between time between these 2 points considered as the period, and reciprocal of that is frequency. Natural angular frequency is 2 pi times f, and sigma, as you see, is not constant value. It is s sine omega t plus theta. The stress varies with time in fatigue test. Key parameters is S that I explained you. If I want to show you, S is here, means the amplitude of the stress, sigma, M, and cycling frequency. And what is this? So S is the stress amplitude. Sigma M is the mean stress. And you see here, sigma max plus sigma mean divide 2. If I want to show you here, it is the sigma m or mean value. And S, that is sigma max minus sigma mean per 2, that I show you is the amplitude here. And about the frequency, I show that it is F, that is reciprocal of period. So fatigue can cause part failures even though applied stress or sigma max less than yield stress, responsible for 90% of mechanical engineering failure. And so it shows the critical role in fracture mechanics, and we should consider that. Fatigue testings can be performed in several ways, depending how the load is applied. For example, axial test means under push or pull loading along the specimen axis, often used for bolts, rods, or welded joint that you see here. The direction here completely tensile or maybe be compressive or push and pull. Okay. Another types of very common fatigue is bending tests, either 3-point or 4-point bendings simulate flexural fatigue as seen in beams, in uh, in beams or brackets. And you see, for example, here 4-point bending. Each of them considered as 1 point. For example, here it is 4-point bending. Another types that in this video we will focus on that it is rotating bending fatigue tests that are widely used for shaft and axles where the outer surface alternates between tension and compression. Means sometimes experience tensile stress, sometimes experience the compressive stress, and changing between them cause the rotating bending. And you see that it is in this form that bending applied to. Another types that we have is torsional test, apply cycling, shear stress, modeling twisting loads in coupling or drive system. Another types that's very important is thermal fatigue. It's very important, caused by repeated heating and cooling, which is common in turbine blades or exhaust component or some things. And so it's very important that we consider the effect of temperature too. But in this video, we will focus on rotating bending fatigue that most widely used tests to determine the endurance limit or fatigue S or SFAT or SN curve that we talk about that in next slides. Okay, rotating bending fatigue test, you see the equipments and um, um, that we need for doing these tests or performing rotating bending fatigue test. Okay, let's look closely at the rotating bending fatigue test. This test help us to determine the fatigue limit or SFAT or fatigue life means N of a material when subjected to cyclic bending stress. The setup typically includes an Ono type rotating bending. It is the rotating bending that you see here. Fatigue machines and cylindrical samples usually have the 6 up to 10 millimeters in diameters, means we are talking about the green sample that you see here. And one end of sample is fixed. If I want to talk about the fixed means this end is fixed. And this end, because of the motor or something, means rotating. So one end is fixed while the other end is rotated. A constant load F is applied using weight on lever arm. If I want to show the force, it is the force that you see that it is F, okay? As the samples rotate, the surface experience alternating tension and compression. Every full revolutions means cycles produce one complete stress cycle from tension to compressions and back to tension again. So in this slide, we talk about the equipments that we use for doing these tests. Now talk about the formula. If you remember from strength of the materials, the stress generated during the bending can be calculated using the following relationship. Means if you consider it is neutral axis, sigma at each point is my per I, or sigma divide y is m per I. What is y? Y is the distance from the neutral axis, okay? Sigma is bending the stress at that point that has a distance as y from the neutral axis. M is the bending moment, means not torque. Torque means at this direction is bending moment. I is the moment of inertia. For circle or for circular cross section is pi d to 4 per 64. R is the radius of the curvature for beam or something, or structures, and E is the Young modulus. So sigma is my per I. If we have the, for example, circular, when we have the maximum stress means here, and you see, for example, here is if the M be in this way, here we have the maximum tension, decrease, and here we have the maximum compression. So sigma max we have here and here, means most distance from the neutral axis. What is this distance? Is R, or diameter divided 2. So sigma max is M d per 2I. What is I? Pi d4 per 64. If we substitute here, we reach to sigma max is 32 M that is bending moment, if you remember. Pi is pi, and d cube is the diameters of the structures or beam or something. Okay, if you remembered, and the distance between force apply here, and this distance is L, moment is F times L, okay? So you substitute here, so we reach to sigma max is 32 FL per pi d cube. It is very important, and you see in the next example how we use that equation. Okay, example. We have the cylindrical ductile cast iron bar is subjected to reverse rotating bending stress cycling, which yields that test result presented in figure this figure. If the maximum applied load, so means we have F max as 1250 Newton. Compute the minimum allowable bar diameter, so we are looking to the mean for this F max to ensure that the fatigue failure will not occur. Assume that the safety factor, or N, is 2.45. And the distance between the load bearing point, or L, is 47.5 millimeter. Okay. It is cast iron. You see here we have different material from the here, for example, for titanium, for 4340 steel, 1045 steels, and here is the ductile cast iron that we focus on that. In this curve, it is the SFAT, or fatigue limit, or stress. If I read that, it's come here, it's about 2020 megapascal, okay? Remember this equation from previous slide, the sigma max is 13 FL per pi d cube. Okay, remember that. Now, because we have the safety factor, sigma divide n, we should consider y. We explained that before, that for avoiding that, or considering that the sample be safe, we shouldn't reach that to a stress reach to sigma per n, means n times smaller than maximum sigma. So sigma per n is 16 FL per pi d cube. If you remember from the graph, we found that SFAT, or fatigue limit, is 220 megapascal. From this equation, D naught cube is 16 FLN per pi sigma. If we are looking for the knot or diameter, it should be this, means to 1 per third, or cubic root. Okay, substitute instead of 16, 16. F is the F max that we had. L is the distance that problem said that 45.5 millimeters. Convert that to meter. And N is the safety factor, sigma is the SFAT or fatigue limit from the curve for cast iron, and pi. And we reach to this meter or 15 millimeter. It should be the minimum diameter that we need that can tolerate this dynamic loading condition. Okay. Understanding fatigue data or SN curve. Fatigue data, when it's plotted as a stress amplitude or S versus the logarithmic of N. N is the number of cycles per failure. So here is the stress amplitude for reviewing so fast. Stress amplitude is this S. Per or versus N is the number of life that we expect that can tolerate that. Two types of fatigue behavior we have. Fatigue limit or SFAT means when the graph reach to horizontals, yeah, means no failure if S less than SFAT. Why? Because here is safe, yeah. If S less than this amount, we cannot expect that how much life it should have, okay? No fatigue limit when you see some curve that is completely curved, not reached to steady state, not horizontal or something, we say no fatigue limit. I'm talking about this one. This, it has fatigue limit, yeah, because it reached to a step, steady. But here is completely curved, not reached to a step, so no fatigue limit. Some materials eventually fails at any stress below sigma ut. For example, it depends to number of cycles. Maybe it reached to, if you continue this, we expect that reach to zero means at any stress, maybe it has the risk that for one N reach to failure. Okay. Fatigue life or NF means total number of stress cycles to cause fatigue failure at given stress amplitude. So what's the meaning? That means if we have the stress, go to the curve for specific materials and we read the N of that one, and it is the fatigue life. Okay. Example 2. Example 2, the problem said that the fatigue data for ductile cast iron are given as follow. It is the stress amplitude in this column as megapascals or inside the parentheses KSI. And cycles of the life means N, yeah? You see here. This one is 10 to 5, 10 to 5, 10 to 6. Okay. How we do that? It's so easy, means curve S versus the logarithmic of that means, for example, the log of 1 times 10 to 5, yeah? Or something. Okay, we curve that and we reach to this graph. So make an SN plot, stress amplitude versus logarithmic cycles to failure using this data. What is the fatigue limit for this alloy? Fatigue limit means exactly when the curve be horizontals, means this point. Yeah, this point, we come here and we read the amounts that, and you see it is 193 megapascal. Part C, determine the fatigue lifetime at the stress amplitude of 230 megapascal. 230 megapascal, it should be this point, yeah? Point A. We read the N related A, and this should be 5 times 10 to 5 cycles, or logarithmic of N 5.7. Okay, the next point is 175, 175 megapascals. Okay, you see that 175, when sigma is less than SF or FAT, n be infinity. Yeah. Why? For example, as n be infinity here, 175 is less than 193, so n should be infinite number. Means we cannot expect how much life never fail or be safe. Any area below this will be safe. Okay, and part D, estimate the fatigue strength at 2 times 10 to 5 and 6 times 10 to 6 cycles. Okay, 2 times 10 to 5 cycles means logarithm of n should be 5.3. 5.3 be B point. B point is this point. Means here we have n and go to the curve and read the stress related this point, and this stress be about 240 megapascals. The next point, 6 times 10 to 6 means n is 6 times 10 to 6. But what is log of n? Log of n should be 6.78. 6.78 means this point. Go to the curve and read the stress related that, and this stress be 205 megapascal. Okay. To summarize what we talk about that today, fatigue failure is one of the most important consideration in design because it occurs gradually and often without any warning if we experience failure. So it's very important to consider the fatigue behaviors of material. Understanding fatigue behavior, especially the rotating bending test that we talk about that today, and how to interpret SN curve helps engineer design safer and more durable components. If this video helped you to understand fatigue, failure, and rotating bending tests better, make sure to like and subscribe for not missing the future videos that will be posted in mechanical property, fracture mechanics, and subjects. Thank you. Have a good one, and bye-bye.